Engineering precision drives large-scale construction projects, where bridge assembly integrates structural design, heavy lifting, sequencing, and rigorous quality control standards. The construction of the Padma Bridge required some of the most challenging underwater engineering works ever undertaken in Bangladesh. At Pier P39, crews carried out the complex task of placing the pile cap reinforcement cage at the bottom of the mighty Padma River, where powerful currents, shifting sediments, and extreme depths created a uniquely demanding environment. To accomplish this, engineers first installed massive steel piles driven deep into the riverbed to reach stable soil layers. Once the foundation was secured, divers, barges, and specialized lifting equipment worked together to lower prefabricated reinforcement cages into position. Because visibility underwater was extremely limited, every step depended on precise surveying, GPS-guided positioning, and constant communication between the surface team and underwater operators. The steel bars for the pile cap were arranged within a large cofferdam-like structure that protected the work zone from turbulent water. After the reinforcement was accurately aligned, high-strength concrete was poured through tremie pipes to form the pile cap, creating a solid base that would eventually support the bridge pier. This underwater operation demonstrates the advanced technical capability, coordination, and resilience required to build one of the country's most iconic megaprojects. The Padma Bridge pile foundation was engineered to ensure exceptional long-term stability, with a targeted service life of 100 years. Its deep steel piles were designed to withstand high-magnitude earthquakes and the extreme geological conditions of the Padma River. Even during the monsoon season, when water flow intensifies dramatically, the structural integrity of the piers remains unaffected, guaranteeing reliable performance for generations. The construction of the Padma multipurpose bridge in Bangladesh represents one of the nation's most challenging and ambitious engineering achievements. According to the documentary Padma Bridge Bangladesh, the project was organized into 5 major components: the main bridge structure, extensive river training works, 2 link roads on either side of the river, and the development of service area infrastructure. Each component was assigned to leading international and national contractors to ensure both technical excellence and steady progress. The main bridge, a 2-tier steel truss structure stretching 6.15 kilometers, was built by China Major Bridge Engineering Corporation. Parallel to this, Sino-Hydro Corporation of China undertook the complex river training operations needed to stabilize the powerful Padma River. Meanwhile, Bangladesh's Abdul Monem Limited was responsible for constructing the link roads and associated facilities, completing the overall connectivity of the project. The bridge stands on 42 massive pillars, each supported by 6 deep piles driven into the riverbed to resist strong currents and seismic forces. Beginning in October 2017, the installation of steel spans progressed with precision, starting with the first span placed between piers 37 and 38. By late 2020, all 42 pillars and the full sequence of 41 spans had been successfully set. The final road slab, installed in August 2021, marked the structural completion of the bridge and a milestone in Bangladesh's infrastructure development. The crossing's development in Adamstown, Dublin, features one of the city's largest precast installation projects, involving the placement of 100 bespoke concrete slabs designed, manufactured, delivered, and installed by Lamyong. The project supports a 3-story car park with retail units on the ground floor. Each slab reached up to 14.1 meters in length and weighed around 9 tons, making them among the heaviest units ever installed on site. Because only 3 slabs could be transported per trailer, more than 300 deliveries were carefully scheduled to ensure just-in-time arrival. Close coordination between Lamyong, the logistics teams, and on-site crews enabled smooth installation and reliable progress, demonstrating strong communication and high technical performance throughout the project. The construction of insulated tilt wall panels plays a crucial role in creating energy-efficient, temperature-controlled industrial buildings. While concrete is an exceptionally durable material commonly used for commercial structures, it performs poorly as a thermal barrier on its own. Therefore, for facilities such as air-conditioned warehouses, builders must integrate insulation into the wall system. A widely adopted method is to sandwich a thick layer of rigid foam insulation between 2 concrete layers, forming an insulated tilt wall panel. The process begins the same way as any conventional tilt-up panel. First, crews build a wooden form on a casting slab, defining the final shape and thickness of the panel. However, from this point forward, the procedure differs from that of a traditional single-layer concrete panel. Instead of filling the entire form with concrete at once, workers place an initial layer of rebar, then pour only enough concrete to cover this reinforcement. This first concrete layer is kept relatively thin so that the insulation can be embedded immediately. As soon as the concrete is smoothed, another team follows closely to place rigid foam insulation sheets onto the still soft surface. Each panel is pre-cut, numbered, and fitted precisely into a matrix, much like assembling pieces of a jigsaw puzzle. After the insulation is in position, workers insert fiber-reinforced composite connectors through the foam and into the wet concrete. These connectors ensure that the insulation bonds permanently to the cured concrete layer and later ties both concrete withes together structurally. Once the first layer cures for several hours, crews return to install additional rebar over the insulation before pouring the final concrete layer. A finishing team smooths the surface in the same manner as the first pour. After full curing, the insulated panels behave just like traditional tilt-up panels. They are lifted upright and set into place using cranes, forming a durable and thermally efficient building envelope. This method provides a strong, long-lasting shell ideal for temperature-controlled facilities and represents the continued innovation of tilt-up construction techniques. Tilt-up construction is a modern building method in which large concrete wall panels are cast horizontally on the job site and then lifted into their final vertical positions using a crane. This approach has become widely used for warehouses, schools, commercial buildings, and even multi-story structures, thanks to its speed, cost-effectiveness, and efficient use of space. The installation process follows a clear sequence that ensures both structural accuracy and on-site safety. To begin with, construction teams prepare the casting surface, which is typically the building's floor slab, or a temporary casting slab. After cleaning and applying bond breakers, they set up formwork according to the panel design. Reinforcement steel, lifting inserts, and embedded hardware are carefully positioned to meet engineering specifications. Once everything is in place, concrete is poured into the forms and vibrated to remove air pockets. The panels are then left to cure until they reach the required lifting strength. Because the panels are cast on-site, crews can work efficiently and reduce transportation costs associated with precast elements. After curing, the lifting phase begins. Before the crane engages, workers inspect the lifting inserts, rigging configuration, and panel edges to ensure safe handling. The crane then slowly raises each panel from the horizontal position, rotating it to vertical while maintaining full control of the load. As the panel swings upright, crews on the ground guide it into its exact alignment on the foundation. This stage requires coordinated communication between crane operators, riggers, and ground personnel to avoid accidents and ensure precise placement. Once a panel is in place, it is temporarily braced with adjustable steel braces. These braces stabilize the wall until the roof structure, floor system, and permanent connections are installed. Proper bracing is essential, especially in windy conditions, as tilt-up panels are tall and relatively thin before being fully tied into the structural frame. With all panels erected and secured, crews move on to installing the roof diaphragm, which locks the entire building together. The final steps involve applying exterior finishes, sealing panel joints to prevent water intrusion, and completing architectural details. Although tilt-up construction offers many advantages, such as rapid project delivery, lower costs, and versatile design options, it also comes with certain limitations. Panel designs cannot be easily modified once cast, and the job site must have sufficient open space to accommodate casting operations. Overall, tilt-up panel installation provides an efficient, practical, and highly effective method for building durable concrete structures while maintaining strong safety and quality standards. The pile-driving work for the Lamyong Bridge project in Banda Aceh involves the erection and installation of 10-meter steel piles with a diameter of 500 millimeters. These piles form the foundation of the bridge piers and are designed to transfer structural loads to deeper, more stable soil layers. The primary lifting and handling operations are performed using a Nisha DH350 crane, which provides the required boom reach, lifting capacity, and stability to work efficiently along the riverbank. Because the river depth is less than 6 meters and the surrounding area consists mainly of compacted fill, the operation does not require the use of pontoons. All equipment can be stationed safely on land. To begin the process, each steel pile section is prepared on the ground, where it is inspected for straightness, weld condition, and surface quality. The crane operator then positions the boom above the pile, and riggers attach the lifting slings to the designated lifting lugs. The erection method applied in this project uses a single support point, or approximately 3/4 of the pile length, allowing the pile to be raised smoothly into a vertical orientation. This method ensures better control during rotation and minimizes bending stresses on the pile walls. Once the pile is upright, it is aligned precisely at the intended pile point. The top of the pile is fitted with a specially fabricated steel pile helmet, consisting of an 80 mm thick plate. This helmet distributes the impact force generated by the pile hammer and protects the pile head from deformation. After alignment, the pile is lowered into its starting position, and the hammering operation begins. The impact hammer, mounted on a leader attached to the crane, delivers repeated blows that gradually push the pile deeper into the soil. In cases where the design depth exceeds the length of a single 10-meter pile, pile extension is required. The joining process is performed using electric arc welding. The top of the driven pile is cleaned, aligned with the next pile section, and welded circumferentially to ensure full penetration and structural continuity. After the weld cools, driving continues until the specified penetration is achieved. The final stage of the operation is determining the depth of the hard soil layer using the calendering method. This method is carried out when hammering resistance significantly increases, indicating the pile is approaching a dense stratum. The process involves measuring the pile's final set per blow using a ruler, millimeter paper, and a pencil. By recording the displacement for every several hammer blows, engineers verify whether the pile has reached the required bearing layer. According to the SPT test results for this project, the hard soil layer is expected at a depth of approximately 32 meters. The calendering data is compared with these geotechnical findings to confirm the final pile depth. Through these systematic steps, erection, alignment, driving, welding, and final capacity checking the steel pile installation ensures a reliable and durable foundation for the Lamyong Bridge structure. The introduction of the newest Quay cranes at the ECT Delta terminal marks an important step in expanding the facility's capacity for ultra-large container ships. After their long sea voyage, the cranes arrive fully assembled on a heavy lift vessel and are carefully positioned alongside the quay at Amazon Haven. The unloading phase begins with securing the vessel and preparing the terminal area. Next, specialist teams use hydraulic skid systems and self-propelled modular transporters to slide the giant structures from the ship onto the quay. This controlled movement ensures the cranes' stability despite their immense height of 142 meters and their lifting capability of 54 meters under the spreader. Once safely on land, the installation phase begins. The cranes are aligned on their rail tracks, and technicians connect the power supply, communication systems, and hydraulic circuits. Each crane features a reach of 25 containers wide, allowing it to handle the world's largest 24,000 TEU vessels. Extensive testing follows, including trolley travel, hoisting, slewing, and remote operation checks. Because these cranes are operated entirely from a remote control center, precise calibration of sensors, cameras, and automated safety systems is essential. The arrival of these cranes forms part of a broader modernization effort at the ECT Delta terminal. Alongside the new equipment, ECT is investing in hybrid automated guided vehicles, hybrid and electric straddle carriers, automatic stacking cranes, and upgraded digital systems. These improvements support the terminal's long-term goal of transitioning toward zero-emission operations. In the coming years, shore power facilities and increasingly sustainable cargo handling equipment will reinforce ECT's position as a technologically advanced and environmentally responsible hub for global container shipping. The project successfully relocated two 100-ton container cranes to the Ferguson Container Terminal using a highly accelerated method designed for an active port environment. Because the operating window was extremely short, specialist technicians from China supported the operation. First, crews installed a steel support structure to distribute the crane's load onto the wharf piles. The cranes were then pulled up a ramp, positioned on cross rails, and lifted by synchronized hydraulic bogies. Despite high winds and tight restrictions, the team safely shifted the cranes into their new working position. The desculling process using the Fractum Model 100 provides an efficient and safe method for cleaning slag pots and breaking red-hot sculls without relying on traditional drop-ball systems. The operation begins with positioning the slag pot in an open work zone, allowing easy access for the hammer system. The Fractum Model 100, mounted on a suitable carrier, is then brought into place. Its high-impact energy output enables operators to fracture large, solidified slag deposits with precision while maintaining a controlled working environment. As the device engages the red-hot skull, it delivers repeated, powerful blows that quickly crack and loosen the fused material from the pot's inner walls. Because the technology transfers energy efficiently through the impact head, it eliminates the need for lifting and dropping heavy steel balls, which traditionally posed risks, required more space, and generated excessive vibrations. Instead, the Fractum hammer breaks the skull in situ, allowing fragments to fall safely to the ground for removal. Throughout the process, operators maintain a safe distance, relying on the machine's extended reach and stable handling. The rapid braking action reduces downtime, enabling slag pots to return to service sooner and improving overall production flow. Additionally, the controlled impacts help minimize structural stress on the pots, extending their working life. By integrating the Fractum Model 100 Steel plants achieve faster, safer, and more cost-effective slag pot cleaning operations. The Bridge 6 reconstruction project near Battersea, London, is a major rail-over-rail infrastructure upgrade designed to replace an aging timber and steel bridge while keeping the vital railway route fully operational. Bridge 6, originally built as a timbered steel structure, had reached the end of its service life and required complete renewal to ensure long-term safety, reliability, and performance. BAM Nuttall was tasked with delivering a new reinforced concrete structure that would be constructed around the existing bridge, allowing trains to continue running during most of the 10-month construction period. This requirement for continuous railway operation shaped the entire methodology and schedule of the project, demanding meticulous planning, staged construction, and precision engineering. From the outset, the project team developed a phased strategy, beginning with the construction of the new concrete sections in the non-railway spans. This approach allowed crews to perform extensive foundation, formwork, and reinforcement activities without interrupting the live railway lines beneath the central spans. By completing the outer spans first, the new structural components could be progressively tied into the existing layout, setting the stage for the more complex works that would follow over the running tracks. Throughout these early stages, BAM Nuttall coordinated closely with Network Rail to ensure every activity complied with strict safety standards and maintained full control of track movements in the surrounding area. As construction progressed, the team transitioned to a period of intensive 24-hour working, during which individual blockades of the lower rail lines were scheduled. These blockades allowed crews to remove old elements, install new concrete components, and carry out track-related tasks in tightly controlled windows. Each blockade required detailed planning, as the lines were to be returned to traffic immediately after each shift. This approach ensured the overall railway network maintained regular operations while enabling steady progress on the bridge replacement. Works manager Tony Russell noted that 3 of the 5 spans had been successfully completed by the mid-project stage. During this phase, teams focused heavily on track installation and stabilization within the sidings. New track panels and fresh ballast were placed, followed by the use of a tamper, a specialized machine that consolidates ballast and precisely adjusts the line and level of the track. The tamper's role was critical to restoring track geometry and ensuring smooth, safe rail operations across the partially reconstructed structure. The most challenging phase of the project was the 9-day Christmas blockade, scheduled when passenger and freight traffic volumes were at their lowest. During this period, crews worked continuously to complete the final 2 spans, remove the remaining sections of the original bridge, and install substantial new track infrastructure. In this intensive window, the project team removed the old timber and steel components and placed 900 millimeters of fresh ballast on the upper line, followed by new sleepers and rail. This large depth of ballast was essential for both long-term track stability and smooth integration with the new reinforced concrete structure. Because the blockade represented the only full closure of the line, every task had to be executed with absolute precision and without delay. The successful completion of these works allowed the bridge to transition from staged construction into full operational readiness. Network Rail Project Manager Phil Leake emphasized the significance of this achievement. He explained that the 9-day blockade during Christmas 2011 was completed not only without any accidents or incidents, but also well ahead of schedule. In fact, the rail possession was handed back approximately 60 hours earlier than the planned release time, a remarkable accomplishment for a project of such technical complexity. This early handback reduced disruption for rail users and highlighted the effectiveness of the collaborative planning between BAM Nuttall, Network Rail, and numerous subcontractors working on site. Beyond the engineering challenges, the Bridge 6 project stands as an example of how modern railway reconstruction can be executed safely in highly constrained environments. By combining innovative sequencing, disciplined coordination, and continuous supervision, the team managed to deliver a fully upgraded rail-over-rail structure without compromising the daily operations of one of London's busiest railway corridors. The transition from a deteriorating timbered steel bridge to a robust reinforced concrete structure ensures that this critical junction will continue to serve the network reliably for decades to come. In conclusion, the reconstruction of Bridge 6 near Battersea showcases the successful integration of technical expertise, strategic scheduling, and efficient on-site execution. The project demonstrates how essential infrastructure upgrades can be achieved through careful planning and cooperation, ultimately delivering a modern, durable bridge that enhances the safety and resilience of the railway system while minimizing disruption to the public.